Okay then, so in this video I want to describe the Mitchell-Benabou language. So this is a very useful language which allows us to convert, the great thing about topos theory is, well, one of the great things is that it's a lot like set theory. It's a sort of generalization of set theory, and the Mitchell-Benabou language allows us to make that connection and basically it's a way of writing category theory so it looks like set theory. So you can use it and you can sort of do set theoretical style proofs, which are very easy to understand. You can express ideas like implies, and, or, not, for all, exists, in, and so on, union, intersection. All of the, you can express all these ideas in terms of the Mitchell-Benabou language, but actually you're talking about general topos theory. So you're talking about what's happening in some general topos, and so you can do logical proofs with it, but you can also, like, it's just very, very nice language. So I suppose the first thing, you can think of it kind of like type theory. So the objects correspond to types, and you have terms. Now, a term is like a load of symbols, I suppose, and there's also special kind of terms called variables. Now, all of these terms have interpretations as arrows. Okay, so basically a type capital X term can be thought of as a sort of arrow into X. Okay, so there's a way of interpreting the terms as arrows, and the basic idea is that we have these variables. Now, each object, each type, if you like, has a list of variables, and we can think of each of these variables as the identity arrow. Now, of course, there's only one identity arrow, but we still allow many variables and they have different names. So, for example, here we have x1 and x2, which are variables of type x, and this is a term. Okay, this is a term of type omega, where omega is the sub-object classifier, because when we interpret this, we interpret it as an arrow into omega. So, okay, we know that the codomain of this arrow, well, at least the interpretation of it, is omega. What about the domain? Well, the domain of a term corresponds to you can find that out by looking at what the free variables are in that term. So the free variables in this one are x1 and x2. Now, I'm saying here that both x1 and x2 live in x, so therefore we can think of this, the interpretation of it, which is when we say the interpretation of a term, we draw these vertical lines next to it. So the interpretation of this term is as an arrow which goes from capital X times capital X to omega. So we can draw it like this. Okay, so if this is our term of interest, phi, we might say that's a formula because it's a term of type omega. It's kind of like has truth values. Okay, so it's like a logic thing, so we call it a formula. Anyway, the interpretation of this is as an arrow So this is the interpretation of phi. It's going to be an arrow, so it takes in an x1 and an x2 and it gives out some truth value. Okay, so this thing here is a term. It has three variables, x1 and x2. This f is just an arrow from x to y, which we're sort of defining externally. And what does this kind of symbology mean with these square brackets here? Well, this is what's called the extension of a term. And what this really is we define it to be the sub-object which is classified by this arrow. You see, because this arrow takes its values in omega, it's an omega is a sub-object classifier. If we pull back true along this arrow, we'll get some sub-object, and we'll call that sub-object S. And this kind of extension formula here says we're talking about this X, and notice that we're putting in sort of what types these three variables have. I mean, this notation x1, x2 is of type X, capital X. That's really telling us about the domain of this arrow interpretation of phi here. Anyway, so okay, interpretation of phi is interpretation of fx1 equals fx2, but what's this mean? Well, this is just shorthand for delta y, open bracket, x1 comma open bracket f x1 comma fx2 close bracket. So I really ought to put the interpretation lines outside there, but because this delta y here is like a kind of variable free arrow, when I'm talking about interpretations, I can just kind of move in the vertical lines that enclose all the stuff that we're interpreting. Anyway, what is this delta y? Well, this delta y is a very useful kind of truth arrow, and it's the sub-object classifier of this diagonal arrow here. So this arrow, identity y comma identity y, is a monic from y to y times y, and this is its sub-object classifier, delta y. So we'll get some experience of using delta y later, but basically it tests when stuff's equal, okay, and it'll give true when the things that you're working on are equal. So basically this will be true when fx1 equals fx2. That's the notation over here, which is really shorthand for this, okay. Anyway, let's continue to, so, you know, I probably ought to have, if I was doing this really methodically, I'd have added an extra term there, and I mean an extra expression there, which would be like this. But since that delta y is just an arrow, I'm allowed, according to the rules of Mitchell-Benabou language, to just move in that line one. And I'm allowed to move it in further past the f's to these x1 and x2. And the interpretation of these, since we're having arrows from x times x, are as projections. Okay, so the interpretation of this is delta y fp1 comma delta y fp1 comma fp2, where p1 and p2 are just the projections, one sending the first x to an x and the one sending the second x to an x, okay. Um, Now, in general, when you're interpreting one of these pairs, you have to think fairly clearly about about um, what the domains are of the stuff inside and what terms are involved and things. But anyway, in this case, it's quite straightforward. Um, so I mean, the bottom line really is that the interpretation of this formula is this: delta y of fp1 comma fp2 close bracket, or we could just write it even more succinctly as delta y f times x, delta y f times f. Okay. So what's going on? I mean, here, well, like we've got the sub-object classifier. This is our true arrow from the terminal object to omega. Pulling this back along delta y, we get this diagonal arrow here, identity y comma identity y. And then pulling this back, we get along this arrow, which we could also write as f times f, this yellow arrow here, we get s. And so in other words, s is the pullback of true along the interpretation of phi. Okay, so in other words, s is the sub-object classified by the interpretation of this phi here. In other words, s is this. All right then, so that's good. I should just say briefly, here I've got just an f. If we have an f and a g here, then we can actually use this notation and this idea to define equalizers. Okay, and that's pretty cool because that means that, because I mean, what you can do then is you can define what a topos is as just a Cartesian closed category with a exponential object. Sorry, yeah, obviously it has it. So and with a sub-object classifier. So in other words, you can define it to be a category that has all finite products, terminal objects, exponential objects, and sub-object classifier. And then you get the existence of limits implied, because you can use this kind of language to define a an equalizer, and then combining equalizers with products, you can get any limits you want. Once you've got all equalizers and products, you've got everything else. So I mean, you've got all the limits, and also you can got co-limits. So there's a paper, something called something like topos theory, co-limits in topos theory or something. You can Google for it and go through this. Also that co-limits exist, co-equalizers and so on. But anyway, co-products in a topos, if you have two sub-objects and their union is two sub-objects of C, and their union is C, and they are disjoint in the sense that their intersection is empty, or equivalently that taking the corresponding kind of truth arrows, doing the and of them gives false, then you then you can define a co-product. Okay, so that gives you all your co-limits, and also that result I just said sheds some light into sort of why co-products work as they do in the category of sets. Now we sort of get a sort of categorical understanding of where co-products come from as well. So yeah, it's all nice, but anyway, let's carry on with this. So we have we've understood a little bit about the interpretation of this formula phi here, but let's make sure we do understand it. So now let's suppose that we have an arrow from m to x times x, say an arrow alpha comma beta. Well then, we're going to have that alpha and beta are going to be in S, this extension here, if and only if doing this, using this sort of interpretation here as our classifying arrow, and doing it on alpha beta gives true. So in other words, if and only if interpretation of f x1 equals f x2 operating on alpha comma beta is true. So this means the truth arrow after the arrow from m to the terminal object, sometimes abbreviated as 2 subscript m. Okay, and anyway, this holds if and only if, you know, just sort of replacing this here with what we boiled it down to, and then putting the alpha and beta inside. This holds if and only if delta y operating on f of alpha comma f of beta is true. So that's as a kind of statement about truth arrows, but we can convert it using the property of the subobject classifier to that's, you know, that is an equalizer. We can convert it to say that this is equivalent to saying that f of alpha comma f of beta is in this monic here, this subobject 1y comma 1y, which is the monic which is classified by delta y. Okay, and that's obviously true if and only if f alpha equals f beta, because this is saying there exists a k such that this is equal to 1y comma 1yk, and that means we have f alpha equals f beta equals k. All right then, so we understand this makes sense really, that something would be in this, you know, if we have an arrow into x, so if we have sort of an alpha arrow from m to x and a beta arrow from m to x, an arrow alpha from m to x, an arrow beta from m to x, then this kind of pair here is going to be sort of contained in this sub-object precisely when f of alpha equals f of beta, and that kind of validates our thinking of this extension here as something like the collection of x1 and x2 in x such that fx equals fy equals fx, such that fx1 equals fx2, excuse me. Okay then, so the next thing is that we want to sort of go up a level to be talking about like sets, well, not sets, but collections of sub-objects. I mean, at this kind of level, we're talking about stuff being equal and things like that, but sometimes we want to talk about the collection of lots of things, and we want to talk about like existential or universal quantifiers, in other words, there exists and for all, and we want to basically be able to use symbols like that, and so the way we do this kind of stuff is to use the power object. So a power object is like basically the exponential when you're exponentiating over the terminal object. So something when you've got like omega to the power of x times x with its evaluation arrow. I mean, technically, I suppose you'd say the power object is omega to the power of x and the evaluation arrow, which goes from omega to the power of x times x to omega. Okay, so we're talking about exponential objects now, and there is some terminology which is useful for talking about exponential objects. I mean, in general, okay, this kind of lambda notation, it's sort of like the lambda notation in lambda calculus, but the basic idea is that you will maybe I can, if I've got a little picture of this, oh yes, here's one. So I mean, we have this interpretation of phi here, and this is like an arrow from x times x to omega. So like for example, if we were thinking in the context of sets, it would be like, oh well, it takes in an input x1 and an input x2, and it spits out some truth value. Okay. Now, I mean, we can also use the exponential object, and then we can say, well, we can take the transpose of this. That'll be an arrow from x to omega to the power of x. We can sort of interpret omega to the power of x as the collection of sub-objects of x, because the points in this correspond to arrows from x to omega, which correspond to sub-objects of x. Okay, but anyway, let's just forget about the fact that this is an omega for a minute. Let's just think it could be any kind of object. So we're talking about in general, for general sorts of like exponentiation. Then we'll have that if we have some term phi here, which has x1 as one of its variables, like this phi does here, it has this x1 as one of its variables, we can write lambda x1 of phi, and that basically changes this into a transpose term. So for example, this type phi here, like let's just forget temporarily that omega is a special thing. Let's just say it's any object. Okay, so this phi here is of type omega, and it has x1 as one of its free variables. But when we write lambda x1 of phi, what we're saying is, well, we're going to convert this into a term of type omega to the power of x. So in particular, the interpretation of this, interpretation of lambda x1 of phi is as the transpose of the interpretation of phi. Okay. Okay, let's remember again now that omega is the sub-object classifier. It is a special object. Okay, so in that case, we have some special notation for lambda x1 of phi, which is this kind of set builder notation. So think of it kind of like the set of x1 in x such that phi. Okay, and we're going to see that there's some kind of sensible, it's kind of sensible to think of it that way. Okay, so now let's just consider this kind of diagram and what's going on. So we've got this arrow interpretation of phi here, which in this specific case we've calculated it to be delta y after f times f, and that's just an arrow from x times x to omega. Now, what we're doing here, we're leaving the x2 alone. So, I mean, you can really think of this kind of interpretation of phi here as a relation, okay? Because it's actually equivalent to, or I mean, it kind of corresponds in this kind of sub-object classifier flipping kind of way. It corresponds to an arrow S like this, which is an arrow into x times x, kind of picking out the kind of, well, if you're in set theory, you'd be picking out the kind of subset of the pairs of things which are related in this way, the pairs of things that make this kind of thing true. These kind of pairs, alpha and beta, such that f alpha equals f beta, that kind of thing. So the way you can kind of think of what happens when we do the transpose of the interpretation of phi on an x1 here is it kind of gives us a set. I mean, if we were talking about in set theory, okay, it gives us a set. So you know, I mean, if x1 was a point of x, this would just be at like a point of omega to the power of x would phi interpretation transpose, and so that would correspond to a set, and we could sort of think of this as this subset of x, which is all of the sort of, has all of the x2s which are in this relation here with our x1 here, okay? So what I'm saying is that I mean, Vertex is a bit fuzzy, okay, but phi transpose like this of x1, this is if x1 is a point of x, This kind of corresponds to the sort of set of all x2 such that x1 is in this relation S here with x2. Okay, it's a bit fuzzy, but hopefully you get the idea. So let's go back from specifics of set theory to general toposes, and we really think of this as the set of as the kind of sub-objects of stuff in the relation S to x1 in the relation S, where this S here is as up here, okay? And then we see when we do this evaluation arrow, I mean, that's we're going from this exponential object here, and we're going from this exponential object times x and into the sub-object classifier. And I mean, the way I like to think of this arrow, again, if we think about it in terms of sets, omega would be like, say, the set true or false. Omega to the power of x, something in there would be like a function which sends every element of x to either true or false, so it's like specifying a subset. X would be like an element, and doing the evaluation arrow, you're sort of saying, is it true that this element's in this set, okay? And if it is, then E will give you a true value down here, okay? But obviously this works much more generally, but basically you can see that this is testing the same thing as this arrow here, whether x1 and x2 are in the relation. The difference here is that we get x1, that's converted to a kind of set of stuff, a set of like x2 style stuff that could be related to x1, and then we're saying is x2 actually in that set, and that's what the evaluator does, okay? So it's nice kind of terminology now. Is that everything there? I think so. Yeah, so these both ways around this diagram give you true if x1 and x2 are in S. And that's a sort of formal statement, you know, actually in this monic, okay? Because, you know, being in this monic is like satisfying this, is like outputting true under this interpretation of phi here, okay? Right, so just again about alternative notation. So when we're doing this, when we want to sort of transpose our interpretation, we can sort of describe this from the kind of language of terms with this kind of lambda notation. Equivalent is this kind of set builder notation. There's some other kinds of shorthand bits of notation. I mean, really, this kind of shorthand is a lot just to make stuff look like set theory, if you like. So, I should say about this evaluation arrow, if we're writing this in as a term, as a kind of type omega term, we'd write it as, I mean, this is a really longhand, E of comma lambda x1 of phi comma x2 all interpreted, okay, because we're actually interpreting it. But this inside the vertical lines is the term, okay. Now notice we have this kind of symbology happening. We have an E after m comma x. Now if you've played around a fair bit with exponential objects, this sort of notation should strike you as strange, because normally you want to be doing an E after something like a transpose arrow times 1, okay? But here we've just got a pair. But that's because this is not an arrow, this is a term. And it needs interpreting. So the projection arrows, the P1 and P2, come in when you do the interpretation of this. And another way we can write this in general, when we're not necessarily talking about stuff that's going into an omega, is as m of x. Okay, so we can sort of think of it as evaluating something, sort of making contact with, with like lambda calculus style notation, I suppose. But anyway, there's an alternative notation when m has a sort sorry, when I say sort, sometimes. I should always say type, okay, really. But sort and type, they kind of mean the same thing. Some people say sort, some people use type when they're talking about the Mitchell-Benabou language. Anyway, when we have a term m of type omega to the x, and we do this kind of evaluation, sort of like what we're doing here, I mean, this lambda x1 of phi here, that is a term of type omega to the power of x, because it's like it has an interpretation as an arrow into omega to the power of x, as we see here. Well, when we have that kind of case, we can rewrite E m comma x as the term x is in m. So it's another kind of shorthand notation that makes some connection with set theory. And of course, as I've already said, we can rewrite lambda x1 phi as this kind of set builder notation, set of x1 such that phi. I put this dot x here. When we do stuff like this, it takes that variable x and it binds it, okay? So it gets bound inside this kind of exponential when we do this kind of transpose, because it then becomes a kind of bound variable inside that transpose thing.